the grating equation. Now we're going to get a bit more mathematical about diffraction gratings. And the grating equation talks only about the directions of the diffraction order. So we don't need to simulate the device to calculate that. So first we'll talk about the grating equation, and then given that, talk about different configurations for diffraction, how you might analyze them. Then to get an intuitive feel about the direction of the diffraction orders relative to grating period, angle of incidence, and other things, we have a series of visualizations and animations that I think will help that. And then in the end, I'll show you how to analyze gratings through the grating equation, and specific examples will be in separate videos. The grating equation. Let's first consider phase matching. Boundary conditions requires that the tangential component of the wave vector be continuous across the interface. So we have an incoming wave, k ints. It has a tangential component, kx ints. We'll call this the x direction, parallel to the interface. And so this component in some way needs to be continuous across the interface. Now, what's different here compared to when we talked about just infinite plane waves at an interface is that the second medium is a diffraction grating. So what on earth happens here? Well, remember from the last lecture, we actually have an array, a whole series of discrete possible directions. And in fact, we have to add and subtract integer multiples of the grating vector from our incident wave vector to account for all these, because now we have multiple directions that the wave can go. So we modify our phase matching condition for diffraction gratings. We still have the tangential component of the incident wave, but here we have this plus or minus integer multiple of the grating numbers or grating vectors. And when I say plus or minus, that's because m goes from minus infinity all the way up to positive infinity. And so we can calculate the tangential component inside the diffraction grating this way. So that's what this means. And so each value of m has a different x component of the wave vector. And assuming we have lossless media, this is always a real quantity. This never becomes imaginary. Now, what about the component in the longitudinal direction or the vertical direction? We talked about tangential. Well, we have to go to the dispersion relation. Remember what the dispersion relation was. We had a wave equation. We solved for the equation of a plane wave. We plugged that solution back into the wave equation, and out came a rule about the wave vector components and how that relates to frequency refractive index. And so given that, we can solve our dispersion relation for that longitudinal component and calculate it this way. So we have a kz squared equals the difference of two things. Now suddenly is the possibility that this number on the right-hand side could become negative, and that would actually make the longitudinal component imaginary. When that happens, we would call that diffraction order cutoff. Here we're going to derive the grating equation. And what you will see is that the grating equation really is the phase matching condition, just expressed a slightly different way. So we start off with what we know. Here is our phase matching condition. We have two terms here. These are tangential components of wave vectors. We would like to write these in terms of their magnitude and angle. So we recognize that the tangential component of the wave vector associated with our diffraction orders is their magnitude times sine of their angle. Likewise, our incident wave vector is its magnitude multiplied by the sine of the angle of incidence. So we can plug both of those into our phase matching condition, and we arrive at a slightly different form of our phase matching condition. Now we see this term k naught appear twice. So what we'll do is we'll divide the entire equation by that k naught term. So the first one drops off, the second one drops off, and in the third term, we're dividing this kx by k naught. For the last step, we're going to recognize that our free space wave number k0 is 2 pi divided by the free space wavelength. Likewise, the tangential component of our grating vector is 2 pi divided by the tangential component of our grating period. And this is something we'll discuss on the next slide too. When we make those substitutions, we arrive at what is called the grating equation. The last thing we will do to this grating equation is account for what is called the grating slant. Notice the grating that I've drawn here is at an angle, and we will label this angle phi. So it turns out when we phase match into this grating, really the only things we need to be considering are the tangential components of things. So we already, in the last slide, wrote the tangential component of our incident wave vector. It's the magnitude of a wave vector in the incident region times the sine of the angle of incidence. Well, what about the tangential component of the grating vector? So we have the grating vector that's perpendicular to the grating planes. The tangential component, or the component parallel to the interface, is along this line that I'm drawing with the laser pointer. Well, that is simply the magnitude of the grating vector times sine of its angle, or phi. We will call this the grating slant. The next thing, we would like to consider this in terms of the grating period. So we'll take this first equation, and we know that the tangential component of the grating vector has to be 2 pi over the tangential component of our grating period. The magnitude of our grating vector is 2 pi divided by the period and times sine. So the equation we've written here in terms of the grating period is the same condition as for the tangential component of the grating vector. Now we can cross off our 2 pi's and we can solve for lambda x. And now we have an expression for lambda x in terms of the overall grating period and that slant angle. So what we'll do is we'll go back to our grating equation from the previous slide, and where there's a lambda x, we will plug in this expression. And what we arrive at, I think, is probably the most general form of the grating equation that you'll find. And this is the form that I've written down and that I use all the time to solve problems. So this is the picture of diffraction from a ruled grating. And we call this planar diffraction because all of these wave vectors are restricted to a plane. We'll talk briefly about when that is not the case, but this is what we'll analyze in this lecture. So we have an incoming wave. It hits something that somehow makes the field periodic. And so we have a periodic field that reflects. We have a periodic field that transmits. So we get diffraction orders on the reflected side and diffraction orders on the transmitted side. And don't worry too much about what is the diffraction grating. It could be bumps on a surface, or it could be a perfectly smooth surface where the wave enters a region that has a periodic modulation in the permittivity. It really doesn't matter. We're just saying that something has chopped up that incident wave and caused it to reflect and transmit. And that causes diffraction orders on both sides. So we would write the grating equation on either side. We're going to have a separate grating equation for the reflected side and transmitted side. And why is that? That is because the refractive index is different on either side. So in fact, we could look at the grating equation and look at this first term of refractive index and just think of that as the refractive index where the diffraction is being observed. So if we're on the reflection side, we'll put in nref. If we're on the transmitted side, we'll put in ntrn. So that's the grating equation. And I like this picture because it summarizes all the different diffraction orders. It shows that you can get a different number of diffraction orders on one side or the other. We'll have more diffraction orders on the higher index side. It also shows you the numbering convention. So these numbers here are the M value, or the diffraction order. Now let's talk more about diffraction configurations. So to this point, we've talked about diffraction from ruled gratings. And a lot of times these are just called 1D gratings, and that's because they're just lines that go in a single direction. But we can have periodic structures or gratings that aren't just lines. They're an array of holes or array of hexagons. And in the plane of the diffraction grating, we can think of that as a two-dimensional lattice. Those lattice has axes or principal directions, and diffraction occurs and follows the grating equation along these principal directions. So here I'm showing kind of a cartoon for a square unit cell, some kind of oblique unit cell, hexagonal unit cell, and I'm showing the planes where diffraction will be most dominant. And the last thing I'll end with is on this slide, is that the grating equation only tells us the directions of the diffraction orders. It does not tell us how much power or the amplitude of those diffraction orders. In order to get that, we actually have to solve Maxwell's equations or simulate the diffraction grating. The grating equation gives us no hints about how much power would go into those diffraction orders. So think of the diffraction orders more as just the possible directions. It doesn't necessarily mean that power will end up in each of those directions. It's just a list of possibilities. Now, this slide is useful when we are analyzing diffraction gratings and simulating them. So almost exclusively, when we talk about the grating equation, we're really talking about planar diffraction from a ruled grating. So the ruled grating means we just have lines, one-dimensional lines running in a single direction. And planar diffraction, everything is happening in a plane. The incident wave, reflected diffraction orders, transmitted diffraction orders, all are in a plane. Now, numerically, when we analyze this, this is very simple. And it becomes a simple equation to analyze, simple configuration to simulate. And there's two different types of modes, it turns out. I like to call these E and H modes. Some people call them TE and TM modes. There's some ambiguity about what's meant by TE and TM, so I prefer E and H. But don't worry about that. Just recognize that there's different modes. Your TE and TM polarizations, they will diffract differently. So this is the easiest case to analyze and what people talk about almost exclusively when they're using the grating equation. Now we could have our incident wave incident at any angle. This is called conical diffraction. We still have a ruled grating, but if we allow that incoming wave to come in at an angle, now suddenly our diffraction orders don't really fall on a plane anymore. Instead they're following some kind of arc, and they're no longer in a plane. That's the important thing. And so numerically, this is a lot more complex. Maxwell's equations don't separate into the two different modes, so it's a much more complicated thing to analyze. Then we can talk about crossed gratings. This is an array of elements, a two-dimensional array of elements. Now here, even if we restrict our incident wave to a plane, the diffraction orders are all over the place. So this is a three-dimensional problem. We can't reduce this to 2 dimensions. And then the last thing, we'll suppose we have any angle of incidence, and really it's not a very different story. The diffraction orders are all over the place. And numerically, if we can analyze the conical diffraction when our incident wave was in a plane, we can also analyze this cone of angles. But when we have planar diffraction from a ruled grating, the math simplifies considerably. So people that are designing diffraction gratings don't necessarily talk in these terms. These are the terms people talk about when they're going to analyze the grating or simulate the grating. And I think this is a very useful way to look at it. We'd like to study the grating equation to try to get an intuitive feel about the directions of the diffraction orders and how they depend on the period of the grating and other things. So following is a bunch of visualizations and animations that I think will be very helpful in that regard. So this slide does not have animations because you're probably looking at a PDF and you can't see animations on a PDF if you're looking at the PDF along with the video. So first, let's have a diffraction grating that is very, very sub-wavelength, a very quick and rapid grating. And what it turns out, there is no diffraction here. We have no diffraction orders. Well, there's diffraction orders, but they're all cut off. So there's really only that zero order. And this behaves just like a standard homogeneous medium. As we start to stretch that and get a longer period grating, suddenly we'll see diffraction orders appear. Now, in this case, they're going to appear first in the diffraction grating because that has the higher refractive index. And when they appear, they will appear first parallel to the interface, and then as the grating period is stretched, these will walk downwards. And this is what I have animations of following this slide, so don't worry too much about it if you're not getting that. But the point is, as we stretch the grating and the period becomes longer, we start to see diffraction orders appear. As we keep stretching it, suddenly we'll see diffraction orders outside of the grating. And if we keep stretching it, what happens is we just get more and more diffraction orders. And at some point we have so many, it may limit what you can do with the diffraction grating. For spectroscopy, we tend to have diffraction gratings that diffract only into a handful of orders. But if we're doing fan-out gratings, like you ever gotten a laser pointer and you screw on those little caps and it makes different shapes, those are diffraction gratings inside there, and they diffract into thousands of diffraction orders, and they're controlling how much power goes into each of those diffraction orders to make an image. Get close to the image, and what you'll see is it's made of tiny little dots. It's not really a smooth, continuous image. And so that's a very, very long period grating. Here is our first of 6 different animations of diffraction from grating. So we are looking at a ruled grating. So the grating is straight lines, if you will. And we have only a normally incident wave. What's happening is we're adjusting the period of that grating relative to wavelength. And in fact, the wavelength shown here, everything's to scale. So you can see the period of the grating relative to the wavelengths. So we have a different refractive index on the transmitted side than we do on the reflected side. There is a higher refractive index on the transmitted side, so that wavelength is a bit more compressed. You'll also notice there's more diffraction orders on the transmitted side because of that higher refractive index. So on the right, I've summarized what we're looking at and some basic conclusions that we can draw from this. One is all of the diffraction orders in the incident wave, everything is within a single plane. Now that would not be the case if our angle of incidence came in and out of the screen in that direction, in which case the diffraction orders would go all over the place. But as long as our angle of incidence is in that plane, that's sort of parallel to the screen here, all of the diffraction orders will occur in the same plane. And you'll see that a little bit clearer in a future visualization, a couple slides from now. So longer periods produce more diffraction orders. The zero order modes, notice they're not even moving here. Those are the same waves that we would get if there was no diffraction grating. So our standard transmitted and refracted waves. And then the last thing to notice is everything is symmetric. The +1 order mode and the -1 order mode, they're basically in the same directions, symmetric about the normal. And I could make the same conclusions about the +3 and -3 order diffracted modes. So I'm going to make these visualizations available on the website, and I recommend downloading those and watching them and staring at them long enough until all of this stuff really becomes intuitive. A few other things to notice. Notice as we're stretching the grating period that those diffraction orders appear first parallel to the grating, parallel to the interface between the reflection region and the transmission region. So I'll use my laser pointer to point. They first appear parallel to the interface. That's when we're stretching the grating. And then from there, they walk down toward the surface normal. They'll never approach that. They just get more and more compressed. But as we stretch the grating, they appear first parallel to the interface and then walk downward. This is the same visualization we had on the previous slide. The only difference is now our applied wave is at an angle. Pretty much everything we concluded on the previous slide, we can conclude here, except the diffraction is no longer symmetric. However, as we stretch the period of the grating, the diffraction orders first appear parallel to the interface and they walk downward. There's more diffraction orders for longer period gratings. There's more diffraction orders on the transmitted side than there is on the reflected side due to the angle of incidence. So everything stays pretty much the same, except the symmetry is no longer there. And that's because our wave is coming in at an angle, and that is not symmetric. Now let's fix the period of the grating and adjust the angle of incidence. And we'll see that everything is still occurring within the same plane. Our applied wave, the reflected diffraction orders, and transmitted diffraction orders, they're all in the same plane. As I mentioned before, if we added an angle component of our applied wave sort of in and out of the screen, then that would not be the case. But as long as everything's in the same plane, in fact, this becomes a simpler problem to analyze. And this is really how we think about diffraction. A bit more advanced topic is the idea of a cross grating. So here it's sort of like we have two ruled gratings superimposed. And we're going to see the same three visualizations we just saw for ruled gratings, but now for cross grating. So in this first one, we have exclusively a normal angle of incidence for the applied wave. But what we can see is the diffraction orders are certainly not occurring within a plane, and they're going in all different directions. So their cross gratings are more difficult to analyze. Everything is still to scale here, the period of the grating relative to wavelengths and all that. So I think that's very useful. And a lot of the same conclusions can be drawn here. The longer the period of the grating, the more diffraction orders. The higher the refractive index, the more the diffraction orders. Now, because our applied wave and the grating itself has symmetry, all of the diffraction orders are also symmetric about the normal. This is the same visualization as on the previous slide, except now we have an angle. All the same conclusions are still there, except we've destroyed the symmetry of the diffraction orders. They're no longer symmetric about the normal. They're not even symmetric about the applied wave. And our last visualization, we will freeze the period of the grating. We won't adjust that. But what we're doing here is just meandering the angle of incidence of the applied wave. And except when that applied wave happens to be at normal, and I'm not sure if it ever reaches that in this visualization, but for all other cases, the diffraction is not symmetric. We will see the number of diffraction orders is approximately the same. Every once in a while, one or two will disappear or appear, so it can vary a little bit with angle of incidence, but for the most part, I would say the number of diffraction orders is relatively consistent. And then we could certainly say that when there's many more diffraction orders. If we only have maybe 3 diffraction orders, the difference between 3 and 2 is quite significant. But for the most part, the number of diffraction orders is not changing here. Diffraction is not symmetric, and it's a neat way to get an intuitive feel of what happens as you change their angle of incidence. Again, I'll make these visualizations available on the course website, and I definitely recommend just watching them for a while until all of this stuff becomes very intuitive. This will help you solve problems if you can picture how they're working. Let's talk about analyzing diffraction gratings using the grating equation. The discussion always comes up about a cutoff wavelength, and that is the wavelength where one of the diffraction orders either pops into existence or it disappears. It's right on that threshold. That's the cutoff wavelength. So typically if we go longer in wavelength, that diffraction order will disappear. If we go shorter in wavelength from the cutoff, we will have that diffraction order. So we tend not to want to operate right on cutoff, usually comfortably to one side or the other. So let's just simplify this. Let's look at the normal incidence case. So that means our theta incident is 0 degrees, and we had an n sine term sitting here, but sine of 0 is 0, so that term disappeared. So our grating equation simplified. Now, we would like to know when the first order modes or the first diffraction orders appear. So what is the cutoff wavelength when this m is plus or minus 1? Well, right at cutoff, the angle of the diffraction orders right at cutoff is exactly 90 degrees. So we would like to know where is theta equal to 90 degrees. So let's plug in 90 degrees for our theta. We set m equal to 1 because those are the diffraction orders we're interested in. And our free space wavelength is now the cutoff free space wavelength. But we have simplified our grating equation. Of course, sine of 90 is 1, so that's 1 equals our cutoff wavelength divided by refractive index and divided by the grating period. We can solve this for grating period, and we see that the grating period is the cutoff wavelength divided by refractive index, cutoff free space wavelength. And so anytime we divide a free space wavelength by a refractive index, we actually get the true wavelength inside the medium. So that is our cutoff wavelength. So what we can see is that we will suddenly have first order diffracted modes when the wavelength equals the grating period. That is the cutoff. So for wavelength longer than the grating period, we have no diffraction orders. Well, we have diffraction orders, but they're cut off. So we're talking about diffraction orders that are not cut off. So when the wavelength becomes less than the grating period, then suddenly those diffraction orders are actual propagating waves. So when the grating period is less than the wavelength, we call that a sub-wavelength grating, and that's actually an interesting topic. That's for another lecture where we'll talk about that. So in conclusion, if we want to prevent first order modes, we need to make sure that our grating period is less than this cutoff wavelength, which, by the way, is the free space cutoff wavelength divided by refractive index. If we want to make sure that they exist, then we just have to reverse this. We need to make sure that our grating period is greater than this cutoff wavelength. Armed with that, we can now figure out what is the total number of diffraction orders. And again, we'll look at the case for normal incidence because it's a little bit easier to analyze. And the answer could change plus or minus a few diffraction orders when we have an angle of incidence. So keep that in mind, but we're not going to be that far off. So let's look at just the normal incidence case. So our grating equation reduces to this. What we need to do now is find the maximum value of m such that our angles don't become imaginary or complex numbers, because that doesn't make any sense. So to ensure that it doesn't happen, we need to make sure that the argument over here is less than 1. And because m can be positive or negative, we're just going to look at the magnitude of this term and make sure that is less than 1. So what value of m ensures this is all less than 1? And that will keep our angle to be purely real and our diffraction orders not cut off. So what is the biggest value of m that does that? Well, we take this and solve it for m. So the maximum value of m is the refractive index where we're observing the diffraction times the period divided by wavelength. So what is the total number of modes? Well, it turns out it's 2 times the number we just calculated plus 1. So in the end, here's our equation for total number of diffracted modes. And very likely we'll get a decimal here. So we will round to the lowest integer. Now, this may be a little strange. Why 2 times m max plus 1? Well, the 2 times m max is there because we have symmetric diffraction. M max just tells us to one side how many diffraction orders there are, but we have plus and minus m, so there's actually twice as many as we're thinking. The plus 1 is there because this m max really didn't account for the 0 order mode, which is actually always there. So we add 1 to that, and that's the reason. Here's a summary of what you need to do to determine all kinds of grating cutoff conditions. So if we want a sub-wavelength grating, in other words, there are no diffraction orders, how do we do that? Well, that's the no first order modes condition. So if there's no first order modes, there's certainly not going to be second, third, fourth, or whatever else. So to do that, we need to ensure that the grating period is shorter than whatever causes the angle at the plus and minus 1 diffraction orders to be 90 degrees. So we will be calculating a cutoff, and we need to make sure that the grating period is shorter than that. Now, if we want to ensure that we do have first order modes, we just reverse that. We need to make sure that the grating period is larger than this cutoff condition. And it's very rare we would operate a diffraction grating right on that cutoff. We'd want to be comfortably to one side or the other. And then we can keep building on this. What if we only want the first order diffracted modes? We do not want second order modes. So let's say we wanted first order modes, but we do not want second order modes. So we're going to have to make sure that both these conditions are satisfied. We'll have to make sure that the grating period is larger than whatever causes our theta or angle for the plus or minus 1 order modes to be 90 degrees. And we need to make sure the grating period is shorter than whatever causes the angle of the plus or minus 2 order modes to be 90 degrees. And so we would have essentially 2 grating periods we'd calculate from that, and we'd want to operate somewhere in between those. So that's really how it is. I know we didn't go through specific number examples, but we'll do that in separate lectures. Just to remind us about analyzing diffraction gratings. When we are using the grating equation, that is the direction of the diffraction orders. So the grating equation tells us everything about the direction. We don't have to simulate this device or resort at all to Maxwell's equation. So the angles of the diffraction orders is very easy. Now, think of the diffraction orders as just what is possible. That doesn't necessarily mean the grating will couple power from the applied wave into that diffraction order. In order to do that, we actually have to solve Maxwell's equations to figure out the polarization of those diffracted modes or how much power is in each one of them. So the direction of the diffraction orders is easy. The amplitude of those diffraction orders is much more difficult because that requires solution of Maxwell's equations. When we talk about ruled gratings or one-dimensional gratings, there's really 3 modes of operation for these. We've been talking about waves coming into this diffraction grating vertically, but what if they're traveling through it this way? And it turns out we call this a Bragg grating, and it sets up your scattered waves are bouncing back and forth, and we get a band of reflected waves, and that's called Bragg reflection. So operating a grating this way, these tend to have very short periods, about a half wavelength. We would get a band of reflection. Throughout this whole lecture, we've had our wave coming in from the side, and what we see is we get diffraction orders that are reflected, diffraction orders that are transmitted. And so this is what we call a diffraction grating. Fundamentally different than a Bragg grating, even though if you're just looking at it without light being applied, they might look the same. There's also something that's talked about a lot less, but a long period grating. And this actually couples energy between 2 co-propagating modes. And we get sort of this band of transmission that's in a different mode. And that's used a lot It's used for sensing to make very sensitive sensors. You can look at long period fiber optic gratings as sensors. This is used in directional coupling and some other things. So This series of lectures is focusing almost exclusively on diffraction gratings, which have a lot of applications, but the exact same geometry can be used other ways, and I just wanted you aware of that.